Okay, let us start a topic in magnetism and matter, that is Coulomb's law. In magnetism. Before we discuss Coulomb's law in magnetism, you should know two things. That is the existence of something called magnetic monopoles. That means usually if you take any magnet, we will have north and south pole as a combination. Like there would be north and south pole as a combination. But in Coulomb's law of magnetism, we will assume that our north can exist separately and our south can exist separately. We will assume that our north can exist separately and south can exist separately, and each one will have a magnetic pole strength of M. This is similar to charge of a bar magnet. So magnetic pole strength M and magnetic pole strength M. Our north pole will behave like a positive charge and our south pole would behave like a negative charge. Then the magnetic here it would be plus M, magnetic pole strength here it would be minus M. If this is the situation, suppose if you have two magnetic monopoles, what does this Coulomb's law states? If you have two magnetic monopoles M1 and M2, what is their pole strength? We don't know. What is their charge? We don't know. The force between them, F bar, would be mu naught by 4 pi M1 M2 by R cube into R bar. This is similar to F bar equals to K Q1 Q2 by R cube into R bar. This is the vector form of Coulomb's law. Just like we have Coulomb's law for charges, we have the force equation between the magnetic monopoles. Now let us look at this formula in detail a little bit. We got F bar equals to mu naught by 4 pi M1 M2 by the distance between them. We have assumed it as R. So it is R cube into R bar. Then what is the direction of this R bar vector? If this is M1, this is M2, I want force applied by M1 on M2, then the R bar vector would be in this direction. That means this would be the direction of R bar if I want force applied by M1 on M2. So this would be the force applied by the first one on the second one. This one also would apply the force in this direction, F2. Magnitude wise, both would be same. F1 magnitude would be equals to F2 magnitude, and this magnitude wise, this force would become mu naught by 4 pi M1 M2 by R cube into magnitude of R bar. So magnitude of R bar is nothing but R. So the magnitude of this force is mu naught by 4 pi M1 M2 divided by R cube into R. R cube into R would become R square. So this is one important conclusion. This is vector conclusion. And one more important thing is that these two forces are having equal magnitude. That means magnitude wise, these two are equal, but their directions are different. If you notice it, this M1 is applying the force to the right. So M2 is applying the force to the left. Since these are vectors, F1 bar is not equal to F2 bar. Remember, vectorially they are not equal because they are pointing in different directions, but magnitude wise they are equal. There is last way to write this. There is one more way, that is F bar equals to, first you will write magnitude and then direction. That means we can write mu naught by 4 pi M1 M2 divided by R square into R cap. The most important thing in this entire thing is, what are the units of magnetic pole strength? This is called as magnetic pole strength, and its units are ampere meter, the most important unit which will help you to determine the units of other things. So the magnetic pole strength is ampere meter. So based on this, he will ask you find the units of mu naught is called as, I think by now you should know this, you have studied in moving charges and magnetism. So mu naught is magnetic permeability of free space. Permeability of free space, and the value is 4 pi into 10 power minus 7. Now we got, Let us continue further. F is equals to mu naught by 4 pi m1 m2 divided by r square. He will ask you find units of mu naught. That means you have to tell what are the units of mu naught. You know its value is 4 pi into 10 power minus 7. He'll ask you find units of mu naught. Let us do that. We know units of f is equals to units of mu naught. For constant, there is no unit. Units of m1, units of m2 divided by units of r square. So units of force is Newton. We still don't know what is the units of mu naught. We are trying to find. This is ampere meter. This is also ampere into meter. That is ampere meter means ampere into meter divided by meter into meter is meter square. So we'll just get Newton is equals to mu naught ampere square meter square divided by meter square. So basically you will get the units of mu naught. So to tell that you are dealing with units, generally we'll use these brackets in this way. So we can write Newton per ampere square. This is the units of mu naught. So if you want to write full value, 4 pi into 10 power minus 7 Newton per ampere square. Since you know units of mu naught, what if I want dimensional form of mu naught? What's a dimensional form? We know Newton is equals to kg meter per second square divided by ampere square. The dimension form of kg is m. Dimension form of meter is L, t power minus 2, a power minus 2. This is the dimensional form of mu naught. Now let us solve one problem based on this. Okay. The question says two magnetic poles, one of which is 4 times stronger than the other, exert a force of 0.1 Newton on each other when placed at a distance of 20 centimeters. Find the strength of each pole. Now let us try to solve it. So we know F is equals to mu naught by 4 pi m1 m2 divided by r square. What is r? R could be distance. In some books you will find a d square. Okay, don't be confused. R is the distance between them. The force is given as 0.1. So 0.1 I will write 10 power minus 1. Mu naught we know 4 pi into 10 power minus 7 divided by 4 pi. And if one of them, two poles, one of which is 4 times than the other. So like if you assume m1 as m, other one is 4 times this. So 4 times this m. So I can write m into 4m divided by the distance between them is given as 20 centimeter. So r is given 20 centimeter. I can write this as 20 by 100. So basically 1 by 5. So or else there is a so we can write here 1 by 5 whole square. You can even write 20 into 10 power minus 2, anything to your convenience. Now I'll cancel these two. So I'll get 10 power minus 1 equals to 10 power minus 7 into 5 square is 25 into 4 into m square. Now let us take 100. So 10 power minus 1 equals to 10 power minus 7 into 100 into m square. So basically m square would become 10 power minus 1 by divided by 10 power minus 5. So you'll get 10 power 4. So based on this, m would be root of 10 power 4. Since m cannot be negative, it would be 100 ampere meter. So m1 would be 100 ampere meter. The strength of the other one, m2, would be 4m. So 400 ampere meter. So this is how we are supposed to solve it. Let us go for next one. Two similar magnetic poles having pole strengths in the ratio 1:3 and placed 1 meter apart. Find the point where a unit pole experiences no net force due to these two poles. So here, two poles are given and their pole strengths are given in the ratio of 1:3. If we assume one of them as m, the other one would be 3m, where m is a constant. We can think one of them is m is a constant. So we have m, and at a distance we have one more 3m. So we have to place one more fellow in between so that it experiences a zero force. So first, let me call this some other quantity, like some third one. Unit pole. Since it is unit pole is given, I'll just call it as some m2 or anything like that. Now first this pole would try to repel it in this direction. This would be because you can think like if nothing is given, we will assume positive pole, and positive north would repel each other. So it would apply a force F1 in this direction. Now this pole also would try to repel this in this direction, F2. Now remember, I'm drawing free body diagram for the center one. So one would apply force in this direction, another one would apply force in this direction. Let us assume the distance between them is x1, the gap between them is x2. Okay, so from this we can write F1 is equals to mu naught by 4 pi m into m2, force applied by m on m2 divided by x1 square. Similarly, F2 would be mu naught by 4 pi m, this is 3m into m2 divided by x2 square. If the net force is zero, the right side force must balance the left side force. That means F1 must be equal to F2. If F1 equals to F2, mu naught by 4 pi m1 m2 divided by x1 square equals to mu naught by 4 pi 3m into m2 divided by x2 square. So if I cancel 4m and 4m, m and m on this sides, so we will basically get, I wrote m1, it's actually m. So it's m value. Now m2 divided by x1 square. This m2 term also would get cancelled on the left side and right side. So you basically get 1 divided by x1 square equals to 3 divided by x2 square. So if I take it to other side, x1 by x2 is equals to root of 1 by 3. So I can write it as 1 by root 3. And not only that, x1 plus x2, what's the actual distance between them? In the question it is given, they are 1 meter apart. That means if I add x1 and x2, the distance between these two is 1 meter. This is a very important combination. We know x1 by x2, which is 1 by root 3. We also know x1 plus x2 is 1. This is called as sum ratio method. How do you find x1, x2? We know ratio of two things, two unknowns ratio we know sum of two unknown things. Then how do you find the individual? If you want x1, the formula is, right now I won't derive this how we got this formula, just remember this, we will use corresponding ratio divided by sum of ratio into sum of unknowns. What do I mean by this? Okay, what is the corresponding ratio? What is the corresponding ratio of x1? The corresponding ratio of x1 is 1. So 1 divided by sum of ratio, 1 divided by root 3 would become 1 plus root 3 into sum of unknowns. What's the sum of unknowns? x1 plus x2 is 1. So you'll get 1 by 1 plus root 3 is the value of x1. Now what is value of x2? Same logic. What's the corresponding ratio of x2? The corresponding ratio of x2 is root 3 divided by sum of ratio 1 plus root 3 into the value of sum 1. So it would become root 3 by 1 plus root 3. So these are the values of x1 and x2. Suppose if you are decided I want to further solve this, x1 equals to 1 by 1 plus root 3 and we want to solve this. We can rationalize the denominator. I can multiply this root 3 minus 1 by root 3 minus 1. If I do that, I will get root 3 minus 1 divided by a minus b into a plus b is a square minus b square. So root 3 whole square minus 1 square. So I'll get root 3 minus 1 by 3 minus 1. So you'll get root 3 minus 1 by 2. So x1 would become 1.732 minus 1 divided by 2. So 0.732 divided by 2. So 0.366. So x1 value would be 0.366 meters. So x2 value would be 1 minus 0.366. So whatever is the value of this, I think it is a 1 minus 0.366. Approximately 1 minus 0.366 if I do 0.634 meter. So this is how we are supposed to solve this problem. And remember, this problem can be extended to many things. What if we have a north pole here and we have a south pole here? What if we have a north and south, not both north and north? What if we have a plus m, here we have minus 3m? If you have plus m and minus 3m, the neutral point, the point where we experience net force will not be in between them. It will be somewhere closer to the smallest one. It will be somewhere closest to the smallest one. We have solved many problems like these in electrostatics. So right now I am not going into this, or else this video would be very, very lengthy. We'll go for the next topic. The next concept is strength of magnetic field. What is strength of the magnetic field? Basically, it is defined as the force experienced by a unit north pole, or you can write unit test monopole. Mostly it would be north only, placed at given point in the magnetic field. What do you mean by this entire thing? Okay, I'll just explain in simple terms. Suppose if you have a magnetic monopole of M, I'm drawing it very large, it would be very small actually. Suppose you placed a unit, so one unit north pole, okay, not just any pole, the test pole has to have one unit, that means 1 ampere meter magnetic pole strength. This is M ampere meter magnetic pole strength. So one unit, and you place that location at this point. So whatever force that this fellow would experience, right now, if nothing is given, this is positive, this is positive, positive, positive will repel. Whatever force this fellow experience, that basically is the strength of the magnetic field due to M at that location. We can say strength of the magnetic field due to M at location of point. In even more simpler terms, if you want to write, B bar would be simply mu naught by 4 pi. We have M1, M2, right? Imagine what if M2 becomes 1. So simply mu naught by 4 pi, M by R square is the formula. And then I can write R cap in vector form. But if you want to write pure vector form, mu naught by 4 pi, M by R cube into R bar. If you notice it, there is no other M here. In force formula, we have mu naught by 4 pi M1 by M2 divided by R square. So you can simply think that you take force between a monopole, like magnetic monopole, and a 1 ampere meter pole strength pole or unit pole divided. Okay, so whatever is this value, its magnitude would be exactly equal to the magnitude of the magnetic pole. Magnitudes are equal, but by definition, the units are not same. If you want to find what are the units of magnetic field, so now let us try to find units of magnetic field. The units of magnetic field, SI units, if you want SI units, it is equals to Tesla. You can use capital T. Remember, whenever you write any unit in full form, everything has to be small. And if it is a scientist name, in shortcut, it has to be capital letter. Like example, Newton, if I want to write, I have to write Newton full form. And in shortcut, I have to write capital N. So SI units would be Tesla and it would be T. Now we know B equals to mu naught by 4 pi M by R cube. We are trying to find the units. You can see these units are similar to F by M also. That means the units of B are similar to units of F by M, because you take the equation of force and just divide by one of the magnetic pole, remove one of the pole from that equation, you get the expression for B. So what are the units of this? Newton per ampere meter. So units of B can be Newton per ampere meter. But we generally don't use this units. We don't use Newton per ampere meter. Very rarely we will use this Newton per ampere meter. But if somebody asks you what is SI unit, you have to tell Tesla only. Then where is this Newton per ampere meter useful? If somebody asks find dimensions of magnetic field. If he's asking us to find the dimensions of magnetic field, in your head you can directly think the dimensions of magnetic field is equals to dimensions of force divided by magnetic pole strength. It is Newton divided by ampere meter. We know Newton is kg meter per second square. So kg meter per second square divided by ampere meter. Meter would get cancelled. You will get m would get cancelled. T power minus 2, a power minus 1. So you can write m power 1, l power 0, t power minus 2, a power minus 1. This is where you can use this formula. You can use it to find the dimensions of B. Now let us go for the next one. See, there is one more unit of, like one more rarely used unit of magnetic field. So that one more rarely used magnetic field is, it is actually Oersted. It is Oersted. Like even though R is there, we don't read it. It is like you read it as Oersted. So this is how we read it, pronounce it as Oersted. So basically, if you want the units of Oersted, one Oersted is equals to 10 power minus 4 Tesla. So this is another unit of magnetic field. One Oersted is equals to 10 power minus 4 Tesla. May not ask in normal examinations, but even if it is, this unit is asked in the examinations, generally he will mention it in the question that one Oersted is equals to 10 power minus 4 Tesla. So no need to remember this value that much. We'll go for the next topic, or we'll solve one problem before going into the next topic. Okay, the question says the moment of a magnet is 0.1 ampere meter square and the force acting on each pole in a uniform magnetic field of strength 0.36 Oersted. So as I told you, whenever this is used, he will tell that this is equals to 10 power minus 4 Tesla. So is 1.224 into 10 power minus 4 Newton. Find the distance between the poles of the magnet. So as given, we know for a bar magnet, the magnetic field strength is m into distance between the poles. We have studied this in the previous topic, distance between poles. And we need to find the distance between the poles. Let me call the distance between the poles as some L. So m is equals to small m into capital L. So this is the first expression. And one more extra information that is given is, when you place this magnet, the force acting on each pole is 0.36. So force on each pole. Suppose you take a magnet and you place it in a magnetic field. So let us say this is the magnetic field and you place it in this magnet. Let us assume this is one pole, this is another pole. So this pole would experience a force in this direction, which is equals to m into whatever is the magnetic field strength at that location, m into b. This pole also would experience it, but it will experience it in opposite direction. Because this will behave like a negative charge, this will behave like a positive charge. So it will be F is equals to m into b. The other is given force on each pole, mb is equals to 1.224 into 10 power minus 4 Newton. From this, we can find what is the value of small m. Small m equals to 1.224 into 10 power minus 4. The magnetic field is given as 0.36 Oersted. So 1.224 divided by 0.36. So 1.224 divided by 0.36. It is close to 3.4. because 3 4s are. So we got m value as 3.4. Now let us substitute here to get the value. Capital M is equals to small m into L. L is equals to capital M value. The magnetic dipole moment is given as 0.1 ampere meter square. 0.1 divided by 3.4. So this is the value of this. So if I do 0.1 divided by 3.4, we are getting this value as, say, made a small mistake. 1.224 divided by 0.6. 0.34s are 1.2. So this is actually 4. I don't know why I have written 3.4. So this would be 4. So 0.1 by 4, I can write it as 10 power minus 1 into 0.25. 1 by 4 is 0.25. The length is basically 0.025 meters. But if you want in centimeter, it is 2.5 centimeter. This is the value of length. We'll go for next one. See, the next concept is magnetic field strength of a bar magnet. So consider a bar magnet, and the first case, let us consider at point P lying on axial line. So we are trying to consider an axial line. So this line is basically the axial line. And imagine we have north pole here, we have south pole here, and distance between the poles is 2a. You might wonder, why are we taking distance between the poles as 2a? Why can't we take it as L? Because in the previous problem we have taken it as L, right? We can take it as L, it doesn't matter. But if you consider 2a, the results will be easy to remember. Like whatever results we are getting, it will be easy to remember. So the distance between the poles is a. Now let us draw a perpendicular bisector exactly here, and this is, let me call this as center. So let this be the center of this bar magnet, and this is the point, some point P, where I am trying to find the magnetic field. Now this is one pole, this is another pole. This is one pole, this is another pole. So I can redraw this entire diagram as, there is this plus M, there is this minus M, and there is a point P. This plus M will try to repel this. That means this plus M would apply a field B1 in this direction. This minus M will try to attract it. So this minus M would attract it with a field B2. What would be the B net at this location? The B net at this location would be B1 minus B2. That would be the B net, because positive would repel, negative would attract. So based on this logic, let me take this to the next page. Now, if this is 2a, the half of this exactly would be a, and another half would be a. Now, all the measurements in these problems, we will do it from the center of the both the poles. From the center of the poles, let us assume the distance is x. If I assume this distance is x, what would be x1? X1 is the distance between, actually the poles would be slightly inside, as we have studied earlier. So let me call this as x1. And from here to here, let me call it as ex2. So based on this, I will get B1 is equals to mu naught by 4 pi magnetic pole strength M divided by x1 cube. Similarly, what is B2? Mu naught by 4 pi M divided by x2 cube. You might wonder, why didn't I write minus M? Because for south pole it is minus M. When we write magnitudes, we will only write their magnitudes also. We won't write plus M minus M. Then why is this minus M useful for? It is only useful to tell the direction of the field at this location. So this minus M is useful to tell the direction of this. Once we get this, so B1 equals to mu naught by 4 pi m by, from here to here it is x, from here to here it is a. If this is x and this is a, what would be x1 equal to? We can say it is nothing but x minus a. Total is x, this part is a. Then what is the remaining part? It would become x minus a. So we will get this as x minus a whole cube. Similarly, not whole cube, I made a mistake, it should be square. So it would be square and square here, and here also it would be square. Similarly, B2 would be mu naught by 4 pi m by x plus a whole square. Think about this. From here to here it is x, this is a, so total would be x plus a whole square. So B net would be B1 minus B2. So mu naught by 4 pi m by m, if I get common, I will get 1 by x minus a whole square minus 1 by x plus a whole square. So you will get mu naught m by 4 pi. So you will get x plus a whole square minus x minus a whole square, and a plus b into a minus b, that is a square minus b square whole square. What is a plus b whole square minus a minus b whole square? It is 4ab. So mu naught m by 4 pi. So I'll get 4ab divided by x square minus a square whole square. So this is the final conclusion that we get. And we know what is 4xa. We know for the given bar magnet of magnetic pole strength m and length is 2a, so we can write magnetic dipole moment is equals to m into 2a. So I can write this formula as mu naught by 4 pi m into, so 2mx divided by x square minus a square whole square. This is the magnetic field on the axial point. And remember, the derivations are not that important if you are preparing for examinations like NEET or even for JEE mains also. If you are preparing for JEE advanced, then these derivations are useful. But for NEET, KCET and all these, the derivations are not that important. It is better if you know it, but no need to practice it. But you have to mug the formula for examinations like JEE mains. Once we have this, let us look at a special case that we asked in examinations like NEET. So we got B at an axial point as mu naught by 4 pi 2mx divided by x square minus a square whole square. If x is much greater than the size of the bar magnet, if x is much greater than it, that means this kind of, that the magnet is very small and the distance that you are dealing is very large. The x value is very large and our magnet size is very small. So this is the situation x greater than 2a means. In this situation, we can also call it as the magnet can be called as tiny magnet. So when we are dealing with tiny magnets or small magnets, we can, this formula can be modified. How this formula gets modified is mu naught by 4 pi 2mx divided by, I can get x square common, x square whole square would come out, 1 minus a square by x square whole square. So you will get mu naught by 4 pi 2mx divided by x power 4 into 1 minus a square by x square whole power minus 2. You will get 1 minus a square by x square whole power minus 2. And we can assume a by x as approximately equal to 0, because if x is very greater than r, you can just take this entire a by x approximately equal to 0. If I take a by x approximately equal to 0, so you basically get mu naught by 4 pi 2 pi x divided by x power 4. So you'll get mu naught by 4 pi 2m by x cube. And remember, So for a normal magnet, the formula is mu naught by 4 pi 2mx divided by x square minus a square whole square. Where this is useful? This is useful for examination like JE Advanced and mains. And in mains also very rarely this is used. But in normal cases, in examinations like NEET and all that, if you want to derive, okay, so B acts, in this case, we will generally have tiny magnets only. So for tiny magnets, A is lesser than X. So B at axial point is mu naught by 4 pi 2m by x cube. This is similar to electric field at an axial point of a dipole, of a tiny dipole. It is K 2 kp by r cube, where r is the distance from the center. Here x is also, see, x, r, d, all these terms are used to represent distance from the center. No need to learn this derivation, just mug the result. Especially if you are preparing for examinations like me, you have to mug this result. It will be very useful. We'll go for next part of this. The next part is magnetic field at an equatorial point, at an equatorial line of a bar magnet. So let us try to derive this. Suppose if you have a bar magnet and I want magnetic field at its any point on the equatorial line. So this is my equatorial line. I want magnetic field at this location. So let me call this as plus M north pole minus M south pole. So this is my north pole and this is south pole. Sorry, this would be my south, this would be north. From here to here, it is A. Again, from here to here also, it is A only. So both are A. And let us assume this distance as some R or X, anything like that. So let me call it as X. Now, what is the distance from this point to this point? Will it attract or repel? So this negative at this point, it would attract. Because when we define a magnetic field, we will assume that the unit pole is positive. So this one would repel it this way with this B1. If you observe it carefully, the distance from south pole to this point is exactly equal to distance from north pole, because this is x, this is a, this is x, this is a. Distance would be root of x square plus a square. Distance, since distances are equal, I can write magnitude of B1 is equals to magnitude of B2. That is one thing we can tell. Now let us continue further. Imagine this angle is theta. If this is theta, with the same logic, this also would become equal to theta. Now, if I resolve the forces into components, I have B1, I have B2. I will call both of them B and B only. Now, let us resolve the upward B into two components. Since this is theta, I can resolve them into B cos theta in this direction and B sin theta in this direction. Again, this B also I will resolve it into components. This is theta. The side to which theta is attached would be cos, B cos theta and B sin theta. As I explained earlier, if you are not preparing for JE Advanced, you no need to understand these derivations in detail. You directly go to the conclusion part of this video and just mug the formulas that we got. Especially this formula is most useful, like where approximation cases we take. Anyway, so B cos theta would cancel. So B net would be 2B sin theta, because B sin theta would add. B cos theta are opposite direction, they will cancel. 2 into mu naught by 4 pi m by whatever, this is x. So what is the distance between these 2 points? So it would be, I will call it as r square into sin theta. Sin theta is opposite side by hypotenuse. So it would be opposite side is a divided by r. Sine theta is opposite side by hypotenuse. Hypotenuse, I'm calling it as r. That's the distance between these 2 points. Now, finally, we got B net is equals to 2 mu naught by 4 pi, mu naught by 4 pi, m by r cube into A. We already know m into 2A is magnetic pole strength capital M. So if I do that, you will get mu naught into capital M divided by 4 pi into r cube. What is r here? You look at this triangle. This is x. This value is A. So this is r. I can write r is x square plus r square is x square plus a square. So r is nothing but x square plus a square whole power 1 by 2. So finally, the net magnetic field at the equatorial point would be mu naught m by 4 pi x square plus a square whole power 1 by 2 into 3. It would become 3 by 2. This is this value. And what is the direction? This is the hero in this. The direction would be, if you notice it, if this is north, this is south, this is the direction of magnetic dipole. Here at this point, the direction of field is anti-parallel to this. This is the hero statement. Okay, so the direction is anti-parallel, very important, anti-parallel to direction of dipole. Now let us look at a special case. So we got B net is equals to mu naught m by 4 pi into x square plus a square whole power 3 by 2. If x is much greater than a, again if x is much greater than a, we can take x square plus a square as approximately equal to x square only. So we will get B net equals to mu naught m by 4 pi into x square whole power 3 by 2. That would be x cube. So this will be the result of the first one. This will be the result of the second one. And most important thing, direction. This is also important. So if we can't remember the entire derivations and all that, directly remember the result of it. So direction would be anti-parallel to direction of magnetic dipole moment. Now let us look at the last case in this. See, the last one would be at any point P. Like let us say we need magnetic field at any point P due to a magnetic dipole. We will take the same results that we obtained in electrostatics. Imagine this angle is theta. We will get two things. One would be B radial, another would be B tangential. So one would be in radial direction, another one would be in tangential direction. Radial direction is mu naught by 4 pi. It is 2 kp by r cube into cos theta. In electrostatics, if you remember, it is 2 kp by r cube into cos theta. In place of k, we have this. So 2m by r cube into cos theta. Similarly, B tangential would be mu naught by 4 pi. Here, we will only take a case where theta is very small. In this case, we will only take a case, that we have in this is, here r has to be much greater than a. If r is not greater than a, this would become very complicated. You won't solve that. We will only take r greater than a case. So m by r cube into sine theta. And B resultant would be, or B net would be root of B radial square plus B tangential square. So you will get mu naught by 4 pi m by r cube into root of 3 cos square theta plus 1. If you substitute everything and do it, this is the final result you will get. But another important thing is there, once you get a resultant, let us say this is B net that you got. What is the angle made by B net with the horizontal? What is the angle made by the B net with BR? So angle made by B net with B radial. Let me call that as alpha. So I will just rotate that so that you can clearly see. Imagine this is BR. This is B tangential. And let us assume this is my B net and it is making an angle alpha. So I can simply write tan alpha is equals to, bring this to this side, BT by BR. BT is mu naught by 4 pi m by r cube into sine theta divided by mu naught by 4 pi 2m by r cube into cos theta. So on solving, you will simply get tan alpha is equals to half of tan theta. This is what you will get. So finally, let me write conclusions, most important conclusions. If you can't derive all these derivations and all that, you just remember the conclusion formula, okay? So what are the conclusion formulae? First, magnetic field on the axis. The magnetic field on the axis of this is mu naught by 4 pi 2m by x square minus a square whole square, and the direction of this, so there is another x here, so direction is along x cap direction, and in special case where x is greater than a, so magnetic field on the axis would become mu naught by 4 pi 2m by x cube into x cap. So if I want to write vectorial, the second one, the magnetic field at equatorial point, it would be mu naught by 4 pi. First I will write only mu naught by 4 pi into m by x square plus a square whole power 3 by 2. This is the expression that you get, and its direction is most important. On equatorial right, the direction is anti-parallel to m bar direction. So whatever is the magnetic dipole moment direction, it would be anti-parallel. That means what is the magnetic dipole moment direction from south to north? This B equatorial on the equatorial line would be from north to south. This will be the direction of B. And in special case, this B at equatorial line would become mu naught by 4 pi m by x cube. X cube, R cube, anything is fine to your convenience. And the last one, in this only special case alone, only we have special case. For a regular case, we can't solve, it will become complicated, where x is greater than a. So we get B net is equals to mu naught by 4 pi m by x cube into root of 3 cos square theta plus 1. This will be the final result, and the angle tan alpha equals to half of tan theta, and then B radial is equals to mu naught by 4 pi 2m by x cube into cos theta. B at tangential would be mu naught by 4 pi m by x cube into sin theta. Okay, the question says a short bar magnet has a magnetic moment of 0.48 joule per Tesla inverse. Find the direction and magnitude of magnetic field produced by the magnet at a distance of 10 centimeters from the center of the magnet. We can see in the question the word short bar magnet is used. That means indirectly is telling us to use those short formula. First one we want at an axial point, because that's the first question we need along the axis. At an axial point we know mu naught by 4 pi, so 2m by r cube or x cube, anything I can write it, both mean the same thing only. So let us substitute the given terms. It would be 10 power minus 7 to 2 into magnetic moment is given as 0.48 and the distance is given as 10 centimeters. So 10 centimeters I can write 10 power minus 1 meters, so 10 power minus 3. So you will get 0.96 into 10 power minus 4 Tesla. Then what is the direction? The direction is same as n cap. That means you can tell the direction is south to north pole. That means if this is my magnet, the direction of m cap would be south to north. Whatever is the location, the direction also of this field would be south to north only. Like it will be south to north direction, or you can simple terms, you can tell the direction of m cap. Now let us go for the B solution of this. We need to find a magnetic field at equatorial point. At equatorial point, since it's a small magnet, we can write mu naught by 4 pi m by x cube. We already know mu naught by 4 pi 2m by x cube is 0.96. Don't again solve it. It would become 0.48, half of this. 0.48 into 10 power minus 4 Tesla. And one more interesting thing is that 10 power minus 4 Tesla can also be called as Gauss. So this is another unit. So 10 power minus 4 Tesla can also be called Gauss. So it will become 0.48 Gauss also. We have seen 10 power 4 minus Tesla is also called as oyster, but the relay. So we also seen 10 power minus 4 Tesla is also called as oyster. Then can we say 1 Gauss equals to 1 oyster? This is not that straightforward. If I start explaining the reasoning behind this itself will become very lengthy one. But anyway, to avoid all these confusions in the competitive examinations, whenever there are other units apart from SI units, he is giving us the convergence. So no need to worry no need to mug these things. They will be given in the examination. Now let us look at the direction of this. So the direction of the equatorial would be anti-parallel, right? Anti-parallel means it will be from south to north is the direction of magnetic field. This would be north to south. So it would be anti-parallel to this. We'll go for next problem. Okay, the question says calculate the magnetic induction at a point 1 angstrom away from a proton measured along the axis of the spin. The magnetic moment of the proton is 1.4 into 10 power minus 26. So what is this concept? Okay, generally if electron or any fundamental particles, very small particles, when they start going in circles, imagine fundamental particles start going in circles, you can assume a fundamental particle like electron, proton going in a circle, as in you can replace this loop with a tiny magnet. We already studied it in moving charges and magnetism topic. You can replace a loop with a very small tiny magnet, and its direction we will determine using right hand rule. So if you assume a small tiny magnet instead of a loop of magnetic moment m, he's asking what is the magnetic field at a distance of x from this. So magnetic field on the axial point, we already know the formula. It is mu naught by 4 pi 2m by r cube. So we will always assume x is greater than anything. So we will get 10 power minus 7 into 2 into m value is given as 1.4 into 10 power minus 26. This is 10 power minus 10 whole cube. So 10 power minus 30. So it will become 2.8 into 10 power minus 3 Tesla, or we can call it as 2.8 milli Tesla. Hope you understood how I have solved. We'll go for next one. Okay, the question says a bar magnet of length 0.1 meter has pole strength of 50 ampere meter. Calculate the magnetic field at the distance of 0.2 meter from its center. If you see, length of the magnet is zero point 0.1, distance is 0.2 meter. So these are not like very far distance magnets. These are not like very far distance magnets. So in this case, suppose if you have a magnet here and a magnetic field on the axial line, it is mu naught by 4 pi 2mx divided by x square minus a square whole square. So this is the formula. Now the distance is given as 0.2 meters from its center, 0.2 meter. So I'll call it as 0.2 is 2 into 10 power minus 1. A is, like we remember, 2a is considered length of the magnet and it is given as 0.1. So from this a would become 0.1 by 2. So you will get 0.5 into 10 power minus 1. So a value, so let us substitute b at the axial point would become 10 power minus 7 into 2 into magnetic pole strength as given as, see, magnetic pole strength is given. So small m is given as 50 ampere meter. So if you want capital M, you will again have to take magnetic pole strength and you have to multiply with the length, that is 0.1 meters, into x value. In place of x, I will write 2 into 10 power minus 1 divided by x square. So 4 minus a square is 0.25. We already whole square. We have already 10 power minus 1 square, 10 power minus 1 square if I bring outside. So you will get 10 power minus 4. So this is the final thing you will get. I'm not solving it, or else if you want to approximately solve this, let us see how are we supposed to approximately solve this. 50 into 0.1, I'll take 5 into 2 2s are 4 into 10 power minus 8. 4 minus 0.25, it is not that big of a number. I'll take it as 4 square only, 16 into, but if I do that, we will get other result. So it would be 3.57 into 3.75 into 10 power minus 4. Generally, these kind of, after this, these kind of questions won't come in competitive examinations. Maybe in boards or something like that, we might get it. So if I solve this, I will use a calculator to get this result. So 20 divided by 3.75 into 3.75, we get a value 1.42 into 10 power minus 4 Tesla. Similarly, you try to solve it along the equatorial line. If you try to solve along the equatorial line, so B equatorial line, we will use a formula mu naught by 4 pi m by r square x square plus a square whole power 3 by 2. If you substitute everything, you will get B equatorial as 5.71 into 10 power minus 5 Tesla, or you can solve it as 0.571 into 10 power minus 4 LS. If you noticed it, here B equatorial is not half of B axial. Earlier we used to get exactly half. Now it is not exactly half. It will be slightly lesser than half of that. So this is one thing that will help you while solving the problems. Here B equatorial is not equals to half of B axial. This is only valid. B equatorial is equals to half of B axial only for which magnets? This is only valid for short magnets. If the magnets are of normal size, like the normal size that we are given here, these concepts are not valid. We'll go for next one. Okay, the question says find the magnetic field due to a dipole of dipole moment 3 ampere meter square at a 0.5 meter away from it in the direction making an angle 45 degree with the dipole axis. So we need at an angle 45 degree with this. If this is my magnet, I want it at some point making an angle 45 degree. Technically speaking, as I told you, this has to be a very tiny magnet. That means this magnet has to be very small. And at 45 degree with this, that's what we need to find. So let us try to solve it. The formula is B net equals to mu naught by 4 pi m by r cube into root of 3 cos square theta plus 1. So mu naught by 4 pi is 10 power minus 7. The magnetic moment is 3 divided by r is given as at 5 meters. So 5 5s are 25, 25 5s are 125. Root of 3 into cos square 45 degrees. Cos square 45 is 1 by 2 plus 1. So 10 power minus 7, 3 by 125. So this would be 1 point, so root of 2.5. So this will be the answer. So if I use calculator and do it, so approximately I'll get 3.79 into 10 power minus 9 Tesla. Another important thing, what is the angle made by the resultant with the radial component? If you want angle made by the resultant with the radial component, tan beta will be half of tan theta. So that would be half. So from this beta would be equals to tan inverse of 1 by 2. How should I represent it? When I represent it, if this is my point P, if this is my B radial, which is making an angle theta, our beta would be making an extra angle with this. This would be my theta. So the total angle would be, total angle with axis would be beta plus theta with x with horizontal axis, like with this. If you want the total angle with the axis, it would be beta plus theta. This is B radial, this is B net. Okay, we'll go for next one. Now let us discuss the very last concept. The last concept would be the what is a magnetic field between two magnetic poles. The question says calculate the magnetic field at point A due to the arrangement of two small dipoles, each having dipole moment of 1 ampere meter square as shown in the figure. So we need magnetic field due to these two. So let us try to solve it. I want net magnetic moment at this location. For this first one, this point A is on the axis. On the axis, what will be its direction? The direction is from south to north. So since it is closer to the south pole, there would be a net attraction B1. And for the second one, this point A is on the equatorial point. And on the equatorial point, the direction is from, so if south to north is the direction of the magnetic pole, it will be from north to south. That means anti-parallel to the magnetic moment. See, this is the direction of magnetic moment. And this is also magnetic moment, same direction. Here, the direction of magnetic moment would be in this way. Here, it would be anti-parallel to that. So this would be B1, this would be B2. So once we find B1 and B2, both are perpendicular. Simply, B net would be equals to root of B1 square plus B2 square. So let us find B1 equals to mu naught by 4 pi 2m by r cube. So 10 power minus 7 into 2 into m value is 1, r value is given as 50 centimeters, that is 1 by 2. So 1 by 2 whole cube. So basically 16 into 10 power minus 7. Similarly, B2 also mu naught by 4 pi m by r cube. All the terms are same because even this one is also same. So it would be 8 into 10 power minus 7. So B net would be root of B1 square plus B2 square, 10 power minus 7 into 8 if I get common. Root, what is left here? 2 is left. So 2 square plus 1 square. So basically you'll get 8 root 5 into 10 power minus 7. This will be the value of B net. So this is how we are supposed to solve at different orientations. Now let us go for the last model in this. The last model is magnetic force between two short magnets. That is, we are not trying to find the field or force between charges or force between monopoles. We are literally finding the force between two short magnets. See, even though I wrote them as short magnets, in the figure I will draw lengthy magnets only, or else they have to be very short. It has to be this much small, so it would be slightly confusing. So that's why I will write it in this way. Let us say this is south and the north, and this is also south and the north, and the distance between their centers, so this center and this center, let the distance between them is r, and let this fellow has magnetic moment m, and this fellow has magnetic moment 2. You can see north and south are much closer, right? Since north and south are much closer, there will be a net attraction between them. Since these two are much closer, you can clearly see that there is a net attraction between them. The force between them would be, just remember the formula, I won't do the derivation here, mu naught by 4 pi 6 m1 m2 divided by r power 4. This will be the formula for this, mu naught by 4 pi 6 m1 m2 by r power 4. So the first case is when they are coaxial. And what is their value? Is it attraction or repulsion between them? Is it attraction or repulsion between them? This will be a net attraction between them. So remember this formula. You can see this force is inversely proportional to 1 by r power 4. The next one, when their axes are mutually perpendicular. So what is the meaning of their axes are mutually perpendicular? So F would be equals to mu naught by 4 pi 3 m1 m2 divided by r power 4. So this would be the axis of the first one. This is how the other one would look. But again, I will repeat, even though I'm drawing them like a very big things, they're actually very, very small. I have to draw one fellow here, another one here, very, very small, tiny magnets, because these formulas are only valid for tiny magnets. And depending upon attraction or repulsion, depending upon how the orientation is there. So these are the forces that we get between them. Now, most important thing that you have to remember is, if we have two monopoles, we got force proportional to 1 by r square. If we have two monopoles, if we got one dipole and a monopole, we will get force proportional to 1 by r cube. If you have two dipoles, you will get force proportional to 1 by r power 4. So this is the important conclusion from whatever we have studied till now. Don't bother about like how we derived this and all this. If you have free time, you can just derive it, find the field that will be acting on this, find the force acting on this, find F1, find F2, and find F1 minus F2. What is F1? F1 would be small m into whatever is the distance between into B1. F2 would be small m into what? Okay, you can try to derive these, but not required. So remember the results for this. And remember this important result. Next, let us solve the one more problem based on this and end this discussion. Two small magnets, each of magnetic moment 10 ampere meter square, are placed in end-on position 0.1 meter apart from their centers. Calculate the force acting between them. First, let us see what is the meaning of this end-on position. End-on position means simply axial position. So that means indirectly saying both the magnets are in this. There is one more position apart from this, that is broadside on. Rarely these are used. I think in competitive examination, even if they use these terms, he will clearly tell what they mean by this. This is basically equatorial position. So one would be in this way, another would be in perpendicular direction. In this case, what will be the answer for this? So we get F equals to mu naught by 4 pi 6 m1 m2 divided by r power 4. Let us substitute everything. 10 power minus 7 into 6 into each one is given as 10. So 10 into 10 divided by r power 4 is 10 power minus 1 whole power 4. So 10 power minus 4. So 6, so we'll get 6 into 10 power. So we have 10 power minus 6. So minus 7 plus 6 is 10 power minus 1 Newton. So this marks the end of all the basics of this. So whatever that is required to understand about a bar magnet, its orientation, and all those we have understood. So after this, we can solve some more problems to understand this concept better.